Welcome back. Now, we are going to look at the many body potentials and some of the other advanced ideas on potential functions very quickly, revise them and get into one of the advanced topic of what we call electronic way of defining or the first principle calculations without making much of an assumptions for the potential function. That is an important advancement that you will see, that we are now going away from simplifying assumptions, but making it more and more complicated. But then with that complication, we are including a lot of these forces, and we are able to give accurate description of the potential function. So, in the many body potential, this started with the failure of the pair potential. So, we said we need to look at all other bodies in the system, and that was done in 84 for metals and alloys. So, we looked at the cohesive energy or property of the conduction electronic charge densities in an empirical fashion that is computationally tractable. I think that is very important, that you look at a whole bunch of conduction electron charges, and then you create a cohesive energy where the atom is sitting. So, in the metallic potential, you have an inner core and a valence electron. So, we are looking at those free electrons that are moving on the conduction band, and they are essentially the valence electrons. They are delocalized obviously. So, the one part is embedding function, which is given. If you look at this slide, you can understand there are two parts to it. One part is embedding function, which is connected with the electron density, and then the other one is pair potential, which is looking at again the Lennard-Jones type. So, one part is looking at the Lennard-Jones type, and another one is looking at the embedding function. So, with that you are able to take care of some of these issues with the pair potential, because the electronic density and that is where the density functional approximation or density functional theory comes into it. Based on the metallic system, you can define the electronic density functions, and you can input that as an embedding force, which is where the cohesion comes into play, and then the other one, which is Lennard-Jones type, takes care of all the repulsion part. So, with that simple idea, Dow and Baskis were able to do very accurate calculations for metals, and they were quite accepted. Of course, there were a lot more modifications later on they themselves did with Foils and Baskis and all of that research that emerged from this seminal paper of 1984. So, that is where the many body potentials came into the being. Then with that, because we are now able to calculate different kinds of system which are metallic system, that is where we started looking also into the strength of the material. We will talk about that later. Now, let us look at some of the bonded materials, and that is important primarily because in a system which has lots of configurational elements in it, like hydrocarbon chains. If you look at a chain of maybe 100 carbon and hydrogen CH, 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 and at certain point they have NH3 group, OH group, and all of those radical groups are connected with the ketones and alkanes and all of those long chains. Then if you look at in the organic substances, we have to consider a lot of actions which are based on the bond stretching, bending, and also rotation. Unlike metals, as you know, things are regular and they are put in lattice structure. They have a very well defined face centered cubic lattice structure, but in hydrocarbons that is not the case. There is a repetitive system, but it is very flexible because it is an organic system. In this organic system or even polymeric system, which may contain some of the hydrocarbon and also inorganic materials in the polymers, that is where you have to worry about different kinds of angles. So, that because they are not using a very simple FCC structure. So, in this case, if you look at one of the popular programs like Ember, they are designed to handle hydrocarbons, and that is where you look at the two body Lennard-Jones charge interaction, which is the Coulomb type. Then you look at the bonding potential for bond stretching, bond angle, and then dihedral angle between different planes, and all parameters are then taken from the experimental values. Once you include all of that, now you have a very nicely defined force field, and you can calculate very complex organic materials in hydrocarbon or hydrocarbon potentials. And that is where we also looked at one of the important substances in the world, water, and we looked at the Toucan and Raman's ST2 SPC, what we call a simple point charge potential, and that is where we looked at SPC, which has become very popular potential model, although there are about 17 different potential model, TIPS 4, ST2, you name it. There are lots of models for water simulation. Some of them will consider water as a triangular element, some of them will make it very rigid. So, there is no flexibility in OH bonds, they are just considered as a rigid molecule with a center of mass, that is an approximation. Or you can have a flexibility as well, and we looked at VMDL simulation on water molecules, where we looked at with the simple potential we were able to look at the hydrogen bond and how two oxygens get connected with one hydrogen bond in between, using the Pauli's rules for creation of the ice structures. So, if you look at simple point charge on your slide, we know it has interatomic potential and intraatomic potential, and obviously interatomic potential is between oxygen and oxygen, because you are looking at two molecules and the heaviest atom there is oxygen, hydrogens are very light as compared to the oxygen atom. So, that is where the interatomic potential between different molecules. But in that case you also have electrical charge, as you know in water molecule oxygen has minus 0.82 electron volts on oxygen, and hydrogen has plus 0.41 electrons. Hydrogen is positively charged, oxygen is negatively charged. So, if you look at these, there are two hydrogen atoms and there is one oxygen. So, if you do twice of 0.41 electron volt, it is 82. So, this is how it becomes electrically neutral, but as soon as you put any ionic substance, then there is a dipole interaction and whole bunch of electrical connectivity happens. In an electrically inert molecule, you can make it electrically charged by adding some of the other ions in it, like sodium chloride. So, if you look at in this case, it is a very well defined potential function, very simple to understand. This is Coulomb part, this is Lennard-Jones part. These are all the expressions of bond bending, bond stretching, bond rotation, dihedral angle, all of those things are going into this long, and each one has a spring constant which is obtained by spectroscopy and some of the experimental methods that we talked about. And then again these are all parameters defined for that potential function. That is when we said, okay, this is a atom where you are looking at oxygen atom and two hydrogen atoms. But now, if you look at silicon, which is another abundantly available material in the world and has really changed the world by creating silicon wafer single crystals and creating electronic devices out of it by doping them. That is where we look at SiO2, where silicon atom is much heavier than oxygen, is connected with two oxygen atoms, SiO2, and that is where we are. What we are looking at is a triangular shape of the atom, primarily triangular shape of the molecule, primarily because it has a tetrahedral coordination. So, there are lots of these small triangles connected to each other and they make a unit cell, and that unit cell gets repeated. And so, that is where we are looking at a model that we should look at silicon and two oxygen interaction as a triangle, and that is where Stillinger and Weber came up with two particle interaction, and then they also look at IJK, 3 particle interactions. So, what are the problems in that? The difficult problem, because potential is highly dimensional function, and if you look at quantum mechanics, then it does not become very easy to solve, and that is where more complicated you make your potential function and add some quantum mechanical effects, then you have to deal with lots of other issues with the calculations. In procedure, if the data are relevant to the system, you need to simulate with similar densities and local environments. So, we are also looking at that you need to have data which is relevant to your potential function, and if you look at quantum effects are present, then you have to account for that. So, there are some of these issues, but by empirical observations or experiment you can solve them, and that is where the success of potential function comes from. Thank you.